Alright, let's look at the derivations for your three most important equations in linear motion. Now, first of all, let's notice that we have this graph. It's a velocity and time graph, so our velocity would be in meters per second, and our time, of course, is in seconds. Now, let's say I wanted to know all the information that's going on between t1 and t2, or this point in time and this point in time. So at this point, I have a specific velocity, vi, and at the final time for this point, I have a specific velocity of vf. So from here, I need to discuss that, or I need to derive our first equation, that acceleration is a change in velocity over a change in time. Now that's pretty straightforward. We've already learned that acceleration, let me pull this up, acceleration is a rate, and it's a rate of the change of the velocity. So when you think of a rate, you need to think, okay, we need to be looking at the slope. So if I wanted to calculate slope of this graph, well, we know y2 minus y1 over x2 minus x1. So here we're going to say, well, acceleration being our slope is going to be whatever's on our y-axis. So y2, vf minus vi, that's y2 minus y1, over x2, which would correspond to tf, minus ti. Now tf minus ti, that's a change or a difference, as is this. But I'm going to write it this way. So we have our acceleration is a change in velocity over a change in time. So there's the first equation derived. Very easy. The second equation we want to look at, though, is a little more difficult. Okay, there are a lot of different variables that we have suddenly introduced. Now, for the second equation, we need to focus on area. So we know this is given x, so that's asking for displacement. Displacement is the area beneath or under the velocity line. So let's start finding the area of this. I'm going to get a different pen color, see if I can do that. Sorry for the pause, guys. Okay, so let's derive the second equation. We need to look at this area. Well, if we make this area into the area of a rectangle, so here's my rectangle, and that area is going to be base times height, and here we have a nice triangle. The area is 1/2 base times height. I should be able to manipulate those variables to where I can get a delta x. So we know delta x, or I'm going to go ahead and say xf minus xi. Now I already noticed that this minus xi, if I take xi to another side of the equation, I get a plus xi. So I like this side already. Now we just need to manipulate a little bit. So let's do this area first. So our base is going to be tf minus ti. That's the base of this rectangle here. I'm going to go ahead and just call that my delta t, or in this case I'm just going to say time. So there's my base. My height would be vi minus 0. That's this distance. And that just is vi. So I like that too, because I already see that there's a vit in my equation. Now the last part is tricky. For my triangle, we know it's 1/2 my base, which is t, we've already said that, times my height, which is vf minus vi. Now my problem here, nowhere in this equation do I have vf. So I need to be able to substitute somehow. Well, we just said that using our first equation, we know A equals VF minus VI over T. I can do some substitution. VF minus VI equals acceleration times time. So now you should see this equation unfold a little bit. I'm going to go ahead, take this to the other side, so it's going to become a positive xi. So xf equals 1/2. Now vf becomes a t. vf minus vi is at. Can't forget this t left over. So now you should see there's the 1/2 at squared. Plus, here I have vi times time. Plus xi. From there, guys, we've done it. xf equals 1/2 a. T times t is t squared. Plus vit plus xi. Okay, last equation. From here, we're going to have to manipulate a lot of variables because we are solving for vf squared. Okay, so the third equation is just a bunch of algebra. This is where I'm trying to get. This is my destination. Now, for the sake of simplicity, we're going to call x. X is the same as delta x, so it's that final minus initial. I need to find a way to square vf. So I'm going to start by using this equation and solving for vf, and then I'm just going to square it. From there, hopefully I can manipulate the variables enough. These are my tools. These are the equations I've already derived, so that's all I can use. I can only use my tools. So let's just get started. VF equals AT plus VI. Now I already see I have a T here. That's not going to be good when I go to square that because I can't have a T in my destination. So I'm probably going to have to do some substitution here. Not fun. So let's see what we get. VF squared then is going to be, we're squaring this whole term. I need to square that. So we're going to have a squared t squared plus 2 ATVI plus VI squared. I did my first and then multiply those together twice and then my last. Now this is good because I have a VF squared here and I have a VI squared here. I need to somehow be able to show that all of this equals 2a delta x. So what I'm going to go ahead and do for this term here, let's see, I'd like to factor out 2a. So we're going to have 2a. Now, if I want to do that, I'm left, if I take a 2a out of this, if I take an a, I'm left with an a. My t squared is left over, but I removed a 2, so now I'm just stuck with 1/2. Now that 1/2 at squared, I've seen that before, so I'm okay with that. If I take a 2a out of this, then I'm left with vi and this t. I've seen that before, so far I'm pretty good. Well, here's 2a. What is 1/2 at squared plus vit? Well, we've said that is x, or delta x. So now I've solved my equation. I'm going to just simplify now. VF squared equals 2a times x, or delta x, plus vi squared. And of course that can be rearranged to say VF squared equals vi squared plus 2ax. Great. We are done with that. Hope you guys like that derivation. I know it's a lot of algebra, but make sure you know and understand and can replicate it for the test. Bye, guys.